They can. All right, so let me just double check, make sure I got this recording. I do, all right. So tonight we are going to talk about probability. We're going to take a kind of a side trip, field trip, so to speak, from statistics for the next couple of weeks. We're going to be talking about the definition of probability this week. We're going to talk about discrete probability distributions next week. Then, of course, we have our midterm. And then we're going to be talking about our continuous probability distributions. So we've got a few weeks of probability ahead of us. Probability and statistics have to be studied together because when we go to estimate population parameters, we have to be able to tell how confident we are in the estimates we get from our samples for the population parameters. And so we're kind of putting a couple of pieces together here that we're building up a couple of pieces that we're going to need to put together in the last half of the semester. So it's going to seem like a totally different class to you today, I believe, topic-wise, but be assured we're still headed on the path toward inferential statistics. So we're going to talk about the basic ideas of probability. So a real important definition that we need to know here is this one. It's about a random event. So a random event, oops, let me change this thickness here. Here we go. This is a little better. A random event is one, meaning is an event in which we do not know what any individual outcome will be, but we do know how a long series of repetitions will come out. For example, if we toss a fair coin, we do not know what the outcome of a single toss will be, but we do know what the outcome of a long series of tosses will be. About half of them will be heads and about half of them will be tails if it's a fair coin. Now, a probability experiment is, how can I say it? A finite number. So in other words, like 10, 20, 30, some finite number of repetitions of a random event. So a probability experiment would be like tossing a coin 10 times. Tossing a coin is a random event. We're going to do that random event. We're going to repeat that random event 10 times. When we repeat a random event, we call it a probability experiment. So the probability of an event, that's what we're interested in defining tonight, is probability. The probability of a random event or of an event is the proportion of times that the event occurs in the long run. So for a fair coin, that is one that's equally likely to come up heads as tails, the probability of heads is 1/2 and the probability of tails is 1/2. Note that the probability never occurs on a single repetition of the event. So if I toss a coin, I'll never get half heads and half tails. I'll either get all heads or all tails if I toss the coin once. It's got to land on one side of the coin or the other. But in the long run, I should have about half of my tosses heads, about half of my tosses tails. And the long run will forever remain a mystery. It's a large number of repetitions. How large? Well, it depends. So we're going to talk about that next, the law of large numbers. Now, the law of large numbers is the foundation of all of our understanding of probability, really. And it's something that the curious among us have just noticed as they observe life. The law of large numbers says that as a probability experiment is repeated again and again, the proportion of times that a given event occurs will approach its probability. And so I'm showing you a little diagram that you'll see, I believe, in your textbook. I kind of wanted to explain it because I think it's a good one. So we've got a graph, we've got actually a time series graph right here. We learned about that a couple of weeks ago. Our time is counted as the number of tosses, so that's how time is passing. So we toss the coin one time, and apparently the first toss was heads, because after one toss, our probability of heads was 1 out of 1. That's where we're getting the 1. So we toss a few tails, our probability comes down. Here, after, about 5 tosses, right here, there we are at 5 tosses. After about 5 tosses, the proportion of heads was 6/10. So it looks like we had, after 5 tosses, we had 3 heads and 2 tails. So 3 out of 5, that's where we're getting that 0.6 from. So now we go on, and after about 100 tosses, right in here, we see after 100 tosses, the proportion of heads was 0.49. So what that's telling us is that we had 49 heads and 51 tails. Finally, after about 10,000 tosses, right out here, the proportion of heads was 0.4994. So we had 4,994 heads and 5,006 tails. So when we look at the proportion, 0.5 or 94, that is really, really close to what we believe the probability of tossing heads should be in the long run, 1/2. But notice something kind of interesting. The difference in the number of heads and tails doesn't behave like we might think it would behave. So after 5 tosses, we had 1 more head than tails. We had 3 heads, 2 tails. After 100 tosses, we had a difference of 2. We had 2 more tails than we had heads. 49 heads, 51 tails. So as our probability gets closer and closer to 0.5, right here we were at 0.49, notice that our proportions are getting closer and closer to 0.5, but the actual difference in the number of heads and tails, they should be equal in the long run, is actually growing. We had a difference of 1 after 5, a difference of 2 after 100 tosses, a difference of 6, 12, I guess. Yeah, a difference of 12 here. 494 heads and 5,006 tails. So looks like we had a difference of 12 right here, 12 more tails than we had heads, but yet our probability was closer to 0.5. Why that happens is because the law of large numbers, the more we repeat the experiment, is actually the large number of repetition that kind of overwhelms any difference and pulls that difference close to, very, very close to 0. So our probabilities are what we would expect them to be. So we're going to make a few more definitions. We need to get acquainted with the language of probability. Thankfully, the language of probability is a lot simpler than the language of statistics. So we won't have nearly as many terms as we had in chapter 1, but we do have a few more that we need to get through. So we have this thing called a sample space. Now, the collection of all possible outcomes of a probability experiment is called a sample space. Suppose that a standard die is rolled. Well, then the sample space is going to look like this. It's going to be a set. So we're going to use our set brackets. And we think of one of those game die that you might see in a game of Yahtzee or Monopoly or whatever board game you're playing. And we know that it's a cube that has 1 dot on one side, 2 dots on another, 3 dots on another, 4 dots on another, 5 dots on another, and then 6 dots on the last side. So here would be our sample space for the probability experiment of rolling a die. It is literally the set or collection of all outcomes that are possible for the random event. So an event, we're going to define this way. We are often concerned with the occurrence that with occurrences that consist of several outcomes. For example, when rolling a die, we might be concerned with the probability of rolling an odd number. A collection of outcomes of a sample space is called an event. Events can consist of a single outcome in the sample space. We call those simple events. or several outcomes in the sample space. We call that a compound event if it consists of several outcomes. So our event of rolling an odd number would be an example of a compound event. The event tossing heads would be an example of a simple event. There's only one outcome in the event that we're interested in. So we're going to take a look at a couple more examples here. So for example, a probability experiment consisting of rolling a die. The sample space is, as we labeled it before, 1, 2, 3, 4, 5, 6. The event of rolling an even number would look like this. We're going to use the set brackets again. And the numbers 2, 4, and 6 are the even numbers in our sample space. So that would be the way that we would note that event. In a minute, we're going to talk about other ways we label events here. So moving on to a probability model. Oh, thanks, Carrie, for letting me know. Glad you could make it tonight. So moving on to the probability model, we're going to define it first. So a probability model is just a table that shows the probability for each event in our experiment. We use the letter P to denote probabilities. So for example, if we toss a coin, we denote the probability that the coin lands heads by capital P, and I like to use the letter, well, I'm just going to write it in here, heads. So when you see the notation that I just wrote down, P parenthesis, heads parenthesis, what that means is the probability of tossing heads. So that's just some shorthand that we're going to use. Oftentimes we name events by using capital letters of the alphabet. So if A denotes the event roll an odd number on a die, the probability of event A is going to be written this way, the probability of event A. So we're just going to put an A in parentheses. And what we know is that A is equal to the outcomes 1, 3, and 5. So it's the event of rolling an odd number on the die. So remember, the probability of an event never applies to a single occurrence of the random event. There's supposed to be an E in there. It only describes the proportion of times the event will occur after many, many, many repetitions of the probability experiment. So we're going to complete the probability model for the experiment of tossing a coin. So what are the two outcomes in our sample space if we're tossing a coin? Good, thank you, Jenna. Heads or tails? So we're going to list all of the outcomes in our sample space. And we said earlier the probability of tossing heads is 1/2. That makes the probability of tossing tails 1/2. Now note we can write probabilities as fractions, we can write them as decimals, or we can write them as percents. There are 3 ways to represent a probability, and unless otherwise instructed, you can choose how you want to represent your probabilities. Oftentimes we ask that you represent probabilities as fractions and then in their decimal form. I know we used to do that on the midterm exam. We don't do that now because the midterm exam is on Connect Math, but on the final exam, and I believe on your application, which we'll look at as well on your application, it's a good idea to represent the probability as a fraction and then give its decimal equivalent, especially if the instructions spell that out. So we're going to talk about special kinds of probabilities. The probabilities that we see, that we have actually in the probability experiment that we're talking about now, tossing a coin. So in our last example, we had a sample space that was made up of two outcomes that were equally likely to occur. So we're tossing a fair coin. So it's equally likely that we'll toss heads as it will be that we toss tails. If a sample space has n equally likely outcomes and an event A has k outcomes, then the probability of A is equal to the number of outcomes in that event A. Of course, we said that that was k. A has k outcomes, divided by the number of outcomes in the sample space. And of course, our sample space, we were told we had n outcomes. So we have n equally likely outcomes. K has, or I'm sorry, event A has k outcomes. So k over n. So we use that thinking up here. In this first event, we had one outcome, heads, divided by the total of outcomes in the sample space, which is 2, heads and tails. And we made the probability for tails the same way. So we were actually using that, that formula quite intuitively. So that brings us to a couple of what I call rules of probability. Not really rules, they're just things that we notice about probability that we're going to use. So the probability of an event is always a number that is between 0 and 1. So we won't have any numbers outside that range for probabilities. We can't get negative numbers for probabilities. We can't get numbers bigger than 1 for probabilities. All probabilities are between 0 and 1. If some event A cannot occur, so what's the probability of rolling 7 on a common game die? Well, there are 0 7s on a common game die. The common game die that I'm talking about has sides that have 1, 2, 3, 4, 5, or 6 dots on them. There is no side with 7 dots on a game die. So we would say that the probability of rolling a 7 on a game die, well, that would be 0 out of 6 because there are 0 outcomes in A. There aren't any outcomes in A. There is no 7. So the probability of when an event cannot occur, then we say that the probability is 0. This kind of leads us to something that we're going to talk about a little later. So when probabilities are very close to 0, then we say that the events that have those probabilities is unlikely. So winning the lottery, for example, winning the lottery, the probability of winning the lottery is not 0, but it is mighty, mighty, mighty darn close to 0. So the probability, my chances of winning the lottery, they're very unlikely. Probably not going to happen. The draw, though, is that very randomly, every once in a while, someone does win the lottery. And so that's what keeps a lot of people playing. You never know, it might be your lucky day. On the flip side, on the other side of the interval, we have the number 1. And if some event A is certain to occur, then we say that the probability of that event A is 1. So if I look outside my window that I'm teaching in my office here, and my desk faces a window. So if I look outside the window and I see it's raining right now, I could say, well, the probability of rain today is 100%. Absolutely certain to happen because it's happening now. So that's what the probability of 1 means. And then, of course, all of the probabilities pretty much that we work with are going to be probabilities between 0 and 1 that we're interested in. So a few more definitions, and then we're going to finally get to working some problems together. So bear with me just a little longer here. So when we talk about sampling from a population, we talked about that a lot during week 1. In fact, your whole application that first week of the course, you had to go out and you had to find a sample study where they selected a sample from a population. A lot of the populations were American adults that you worked with. So we looked at that activity, this sampling from a population, we looked at that in a lot of detail during week 1. So when we sample an individual from a population, that in and of itself is a probability experiment. The population is the sample space, and the members of the population are equally likely outcomes. So let's look at an example of that. We have 792 college students are randomly selected and asked if they started attending college right after graduating from high school. The parents of these randomly selected college students were also surveyed and asked if she had earned a college degree. So the results are given below. So here is our group of 792 students that we have. This is what we're going to call, for purposes of this probability experiment, this is our population. If you did not take the survey, you are not going to be selected. We're only selecting from these 792 students that we randomly selected. So what is the probability that a randomly selected student from this population attended college right after graduating from high school? Well, we're going to use the formula that we just talked about. The probability of event A is equal to K over N, where K is the number of outcomes in A. So what is A? They attended college right after graduating high school. That's our event A right here. Let me just highlight it. That's what I'm calling A right there. So how many of our students attended college right after graduating from high school? Just look at my table there. Yeah, 465. So started college right after high school. We're looking at that total of 465. So there are 465 students in event A. And what is the total number of students in our sample space? How many students? Yeah, 792. Thank you. So there's the fraction probability, or the probability in fraction form. Now, if I put that on my calculator, I'm going to get 0.587. And I'm just going to round my probabilities to 3 places. I've noticed that that's often what you're asked to do when you're working on an application problem. You know, you're working on an application assignment, or on the final exam, the instructions will say, write the probability as a fraction, and then write it as a decimal rounded to 3 places. So I kind of try to mimic that for you. So it just kind of seems kind of natural for you to do that when the time comes. You know what I'm going to say about Connect Math. Just follow whatever instructions Connect Math gives you. Just follow those. But this is the way I've tended to see assignments and exams written. So what is the probability that the parents of a randomly selected student from this population did not earn a college degree? So I'm going to call this event B. I'm just going to use a different letter so we don't get it confused here. So let me see, where is it? Parents did not earn a degree. That's what I'm calling this event B right here. So how many outcomes are in our event B here? How many of these students had parents who did not earn a college degree? Well, neither parent earned a degree. So what is the total number? We're talking about the 792. Yeah, so the total number is going to be this. We're going back to the full sample space again. So we're not talking about the group that we had just talked about in the first example. We're going back to the whole 792. Yeah, so we've got 512 of our 792 students whose had neither of their parents earned a degree. And again, the number in our sample space is going to be that 792. So that's going to remain the same for a good number of our probabilities here. And if I put that on my calculator for my decimal, I'm going to get 0.646. for my decimal representation for that. So you kind of see how this sampling from a population is a probability experiment, and it's a probability experiment that has equally likely outcomes. It's equally likely that we'll select any one of these 792 students that we have in our sample space. So let's see, looking at the next definition, unusual events. An unusual event is one whose probability is small. Remember, we said earlier that when probabilities are close to zero, then those events are unlikely. In fact, we're going to call those events unusual events. And we're getting ready to define here what we mean, how close to zero you have to be in order to be considered an unusual event. So a rule of thumb is that any event whose probability is less than 0.05 is considered to be unusual. So you're going to have some questions like this on Connect Math this weekend. So I want, or this weekend if you do it then, but this week as you're working on it. So I wanted to work on a problem like this with you so you kind of know what's going on here. So is the event at least one parent earned a college degree and delayed attending college an unusual event? So we've got a couple of things going on in this particular problem here. I'm going to get a different color for that table. We have what we call a compound event. So at least one parent earned a college degree. That would be this group right here. Whoops, let me see if I can get this position so we can see the table right here. Yeah, so we're talking about at least one parent earned a college degree and the student actually delayed attending college. So we're talking about, whoops, sorry, we're talking about this group right here. So, and we're talking about the overlap. Looks like there are 29 students who fall into that category. They themselves delayed attending college, attended it later, but at least one of their parents had earned a college degree. So those 29 students, those are the students in our event that we've described here, which happens to be a compound event. So we've got 29 out of the 792 students who are in our sample space. And of course, when I put that on the calculator, what do I get? What do I get when I put that on my calculator? To 3 places. Make sure you guys aren't having any trouble with that. Thank you, Jennifer. Yep, we've got 0.037. And Chris, good, thank you. Is this unusual based on our definition that we just made? Yes, it is. It is unusual because the probability of the event that we just calculated is less than 0.05. So anytime I get a probability that's less than 0.05, and if I want to, I can write 0.05 as 0.050. The reason I'm going to do that is because my probability was written to 3 places. So I can look at that and say, yeah, 37 is less than 50. My probability is less than 0.05. So that's my explanation right here. It's actually the definition. My explanation, whoops, I'm sorry. My explanation right here, the probability of the event that I calculated is less than 0.05. All right, well, I said that we had the probability of a compound event in this last example. So we're going to look at compound events in a little more detail here. So a couple of definitions and a new formula. So a compound event is an event that is formed by combining 2 or more events. One type of compound event is of the form A or B, some event A or some event B. The event A or B occurs whenever A occurs, whenever B occurs, or A and B both occur. whenever we see the word or, our rule for these compound events that are formed with the word or involves addition. So when you see the word or, you kind of want to think add. I'm going to be adding some probabilities here. So here's our rule. For any two events, A and B, the probability of A or B, we compute by doing this. We take the probability of A, we add it to the probability of B, but then we subtract any one that we've double counted. We're going to have to subtract the probability that A and B both occur at the same time. And you will see why this works in my next example. So we need to find the probability that a randomly selected student started college right after high school or had at least one parent who earned a college degree. So according to our general addition rule, the probability of attended right after high school or parent with a degree is going to be the probability of attended right after high school plus the probability of at least one parent with a degree minus the probability of attending right after and at least one parent with a degree. So I know this is pretty sloppy, but I'm just kind of writing in what we're going to be looking for on the table. So we want the probability that the person attended high school or college right after high school. Well, lo and behold, that was one of the first probabilities we found, right? What is the probability that a randomly selected student from this population attended college right after graduating from high school? So we already have that. It's 465 over 792. So I'm going to write that down. That's the first part. And I'm just going to use that blank as my fraction bar. Plus the probability that the student has at least one parent with a degree. So let's see if we have that one. No, we don't, so we have to form that one. So what is the probability that a randomly selected student has at least one parent with a degree? Alex, you're going to see in a minute that it doesn't just cancel out here, I think, if I understand what you're saying. So just hang on, I'm going to show you in this example here. So let me get kind of my earlier marks away from here. All right, so starting with a clean table so we don't get too confused. I want the probability that a randomly selected student has at least one parent who's earned a college degree. So what is that fraction going to be in its unreduced form? So look, good. Thank you, Jennifer. We have 280 students who have at least one parent with a degree divided by 792. So 280 students out of the 792. That's going to be our second probability. So now I'm going to show you why we have to subtract. So we took all of these people in our second probability. We took all of these people, whoops, sorry, here we go. Yeah, all of these people in our first probability, because remember we had 465 over 792 plus 280 over 792. Guess what? These people right here, these 251 people, they were a part of this 465. They were also a part of this 280. They got counted twice. Now, I'm not going to argue that maybe these 251 people are very, very special people. Who am I to say? I don't know. But it doesn't matter how special you are, or how talented or gifted or lucky or whatever you are. You don't get to count anybody twice when you're taking probabilities. You can only count people once. So because we counted these 251 people twice, we have to take one of those counts out. So we're going to have to subtract 251 over 792 because we counted these people twice. And guess what we call that? That's the and part right there. These people started college right after high school, and they also had at least one parent who earned a college degree. So that's why we have to subtract it out. Thanks, Alex, for that feedback. I was hoping it would make sense once I got through the example here. So we have to subtract out that 251 out of 792. And so when we've got like denominators, so we can just add 465 plus 280 minus 251 is going to give us 494 over 792. And if I put that on my calculator, I'm going to get 0.624. So that's the general addition rule right there. And again, we're going to practice, a little bit of this as we go along. We're going to do a bit of practice tonight so you can just get kind of comfortable with these types of problems. We're going to make another definition. That's of mutually exclusive events. So two events are said to be mutually exclusive if it is impossible for both events to occur at the same time. So we see here a Venn diagram of mutually exclusive events. So let's say my experiment is, I want to go back to something simple. I'm going to roll a die. So my event A is going to be to roll a number that's less than or equal to 2. Event B is going to be to roll a number that is greater than 3. So in event A, I've got the outcomes 1 and 2. In event B, I've got the outcomes 4, 5, and 6. And out here, outside both events, is the outcome 3, because 3 was not in event A, it was not in event B either. So here is an example of mutually exclusive events. The example that I gave you, rolling a number that is less than or equal to 2, that was event A. Event B was rolling a number greater than 3. Those are mutually exclusive events because they cannot happen at the same time on a single roll of a die. So events that are not mutually exclusive, I'm going to give you an example of that so you can understand what's going on here. So again, we're going to roll a die. And now my event A is going to be roll a number that is, let me see, greater than or equal to 2. And B is going to be to roll a number that is less than 4. So there's my event A and B. So event A is going to contain the numbers that are greater than or equal to 2. So it's going to contain 2, it's going to contain 3, it's going to contain 4, 5, and 6. Event B, this circle B, there are all the numbers that are less than 4. Well, the numbers that are less than 4 on the die, sorry about this, are the numbers 1, 2, and 3. So here, event A and B together, they form the whole sample space. We haven't left any numbers out of these events. But here we see that A and B can occur at the same time if I roll a 2 or if I roll a 3 on the die. Both events A and B will have occurred. So these are an example of events that are not mutually exclusive. So let's take a look at another example. A die is rolled. Event A is that the die will come up a 3. Event B is the die comes up an even number. So A is going to contain the outcome of 3. B is going to contain the outcome of 2, 4, and 6. So we could say that these events are what? What would we call these events? Yeah, mutually exclusive. Thank you, Alex. All right. So a fair coin is tossed twice. Event A is that one of the tosses is heads, and event B is that one of the tosses is tails. So we need to analyze these events. So event A says that one of the tosses is heads. So event A is going to consist of heads, heads. There we have one of the outcomes is heads. Actually, both of them are, but one of them is. And then it's going to be the outcome of heads, tails, or tails, heads. So those are the three outcomes that are in event A. We could toss heads twice. That has one head. One of the tosses are heads. That's a true statement for that outcome. We could toss heads first, then tails. We have one head in that outcome. Or we could toss tails first and then heads. We've got one head in that outcome. Now event B is that one of the tosses is tails. So for event B, of course, we've got our tails, tails outcome. We toss tails on the first, tails on the second. So one of the tosses was tails. We could toss tails on the first, heads on the second. That would give us one toss of tails. Or we could toss heads first and tails second. That would give us one toss of tails. So are these events mutually exclusive or are they not mutually exclusive? Yeah, they're not mutually exclusive. They have some overlapping. So these two outcomes right here are the overlapping outcomes. That's where they'll overlap. So if we were to draw a Venn diagram of these right here, event A would be heads, 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 tails, tails, heads. That would be our event A. Our event B would be tails, tails, heads, tails, heads, heads. And so we would have this overlapping portion right here. So they're not mutually exclusive. All right, so we've got an addition rule for mutually exclusive events. If A and B are mutually exclusive events, then our rule's a little simpler. We don't have to worry about double counting because A and B cannot occur at the same time. So there's not going to be any overlapping. So all we have to do is take the probability of A and add it to the probability of B. We don't need to worry about taking out any double counts because there is no overlapping of the two events. So let's take a look at an example of that. In the 2008 Olympic Games, a total of 11,028 athletes participated. Of these, 596 represented the United States, 332 represented Canada, and 85 represented Mexico. What is the probability that an Olympic athlete chosen at random represents the US or Canada? So or, of course, says that we have to add. So we need the probability that they represent the US, or that's adding the probability that they represent Canada. And because in the Olympics, a single athlete cannot represent two countries at the same time, these would be mutually exclusive events. A single athlete can only represent one country. So we don't have to worry about taking out the people who represent both Canada and the United States in the Olympics because no one does that. So what is the probability that they represent the United States? Can anyone give me that fraction? Yeah, thank you. 596 out of 11,028 plus the probability that they represent Canada. Good, that's a part of it. 332, what's the rest of it, Alex? Because remember, probabilities always have to be between 0 and 1. There we go, divided by 11,028. Yep, they always have to be numbers between 0 and 1. And that's it. We don't have to worry about double counting anybody. So when we add our two denominators, our two numerators together, 596 plus 332, we get 928 out of 11,028. And when I put that on my calculator, I'm going to get 0.084 to 3 places. So there's my probability. All right, another definition. We've kind of got the whole chapter is pretty much, at the beginning part anyway, is a lot of definitions followed by examples. So we're going to talk about complements in our next example. And so I'm going to give you an example of it first. If there is a 60% chance of rain today, then we understand that there is a 40% chance that it will not rain. The events rain and no rain, or will not rain, are complements. Now, I know I had a spelling teacher way back when I was in elementary school who told us that complements with an I in there between the L and the M, those were nice things that people said about I, about me, or about you. So we could kind of say, okay, if I's in there, that's a nice thing that we say about, you know, it's what I like to hear, compliments about myself maybe. If it's a compliment spelled with an E between the L and the M, we understand that this means they're completers. That's what we're talking about. So the complement of an event says that the event will not occur. And if I put an event together with its complement, I get the complete sample space. So what can happen on any given day? It will either rain or it will not rain. That's all that can happen. You know, if it's sunny, but it doesn't rain, then we're in the not rain category. If it's snowing, then we're in the not rain category. So yeah, it can either rain or not rain on a given day. And when I put those two events together, I get the complete sample space. So the complement of A, we're going to have a certain symbol for it. It's A with a subscript or superscript of C. And the probability then of the complement is going to be the probability of A with a superscript of C. So in our example, no rain, that was 40%. The probability of rain, we're going to call that A, that was 60%. So notice what happens when I add the probability of an event to its complement. What do I get? Yeah, I get 1 every single time. Because remember, when I put an event together with its complement, I get the entire sample space. What's the probability that some outcome that's in the sample space is going to occur? That's absolutely certain. That's all that can happen. So that probability is 1. So if I want to find the probability of the complement of some event, all I have to do is take 1 and subtract the probability of that event from it. That automatically gives me the probability of its complement. Now this is what we call the rule of complements. We're going to use that in our application. We're going to be using that in one of our problems here. But I want to give you an example that I hope will be very intuitive. So I read this about Franklin University a few years back, that 65% of the students at Franklin University take at least 1 online class. So giving you that information, 65% of the students at Franklin University take at least 1 online class. What's the probability that I select a student from Franklin University that takes no online classes? Yeah, 35%. It should be pretty intuitive. The complement is the rest of them. So if 65% of the students are taking an online class, 1 or more online classes, then the rest of them, 35%, are not taking any online classes. So hopefully it should be pretty intuitive to you. So here's an example. According to the Wall Street Journal, 42% of the cars sold in May of 2000 were small cars. So probability of small cars, 42%. I'm just going to write that as a decimal. What is the probability that a randomly chosen car sold in May 2008 was not a small car? You got it, 58%. Thank you. Yeah, it's just going to be 1 minus 0.42. If 42% were small cars, then the rest of them, 1 minus 0.42, were not small cars. 58% were not small cars. So I did this over winter break here. I finally got a new car, and I got rid of my small car and bought a big car just because it's too hard to get out of the small cars anymore. So I went from the small car to the big car. Missing the gas economy that I had, but sure liking getting in and out of that car. It's a whole lot easier than it was in my small one. So we're going to take a look at conditional probabilities next. And so a conditional probability, let me give you an example first so you can kind of understand the idea of it, and then we'll look at some numerical examples and some formulas. So approximately 15% of adult men in the United States are more than 6 feet tall. Therefore, if a man is selected at random, the probability that he is more than 6 feet tall is 15% or 0.15. Now, assume that you learn that this randomly selected man is also a professional basketball player. With this extra information, the probability that the man is more than 6 feet tall becomes much greater than 0.15 because professional basketball players are very tall in order to be good. So a probability that is computed with the knowledge of additional information is called a conditional probability. Oops, my eraser's not working tonight. The conditional probability of an event B given an event A. So B would be being more than 6 feet tall. Event A would be being a professional basketball player in our last example. So that's what we're talking about. The way we write that down, we write it this way. The probability of being more than 6 feet tall, that's our event B, given, that's what this vertical line stands for right here, given that the man is a professional basketball player. That's event A. So this was event A, and more than 6 feet tall was event B right here. There's our event B. And is understood to be the probability that B occurs, the probability that the man is more than 6 feet tall, under the assumption that he's a professional basketball player, that A has occurred. So I'm just going to give you the formula for computing this. The probability is computed. The probability of B, given that A has occurred, is the probability that both A and B occur. That should make sense. If we want B to occur and we know that A has already occurred, then we're wanting the probability that they can both occur at the same time, divided by the probability that event A has occurred. So here's the formula for the probabilities. The way we're going to use this most of the time, we're going to use this with equally likely outcomes. So when the outcomes in the sample space are equally likely, then the probability of B, given that A has occurred, is the number of outcomes in the event A and B, in the overlapping of those two events, divided by the number of outcomes in event A, all by itself. So we are going to look at this in this table right here. And you're going to see some, you're going to see some of this work on Connect Math. So let me kind of get this up to here. We can do the first couple and see everything we need to see. So here's our example. Consider the following table, which presents the number of US men and women in millions, 25 years old and older, who attained various levels of education as of March 2007. So this was taken from a census, most likely, back around, I don't know, would have been 2006, whenever that census was taken. 2000 maybe. So anyway, this is probably coming from a census. So the first row is for our men. So we see that we have a total of actually 94 million men in our example. So 14 plus 29.6 plus 15.6 plus 7.2 plus 17.5 plus 10.1. If we were to add those all together, we'd get 94. In the second row, we have women. So tell me how many women we have in our sample, how many million women we have in our sample. Yeah, thank you. We have 101 million women. Good. Just adding those numbers across the row like I showed you. All right, so that means that we have 195 million people in our sample space. Some are men, some are women, and of course these are in millions. Tells us in our problem right up here. That's not going to matter because we're just going to count everything in millions. So how many people were not a high school graduate? Well, I can do that pretty easily. 14 plus 13.7 is 27.7. High school graduates, looks like we had 5, carry a 1, 61.5. Some college but no degree, went to college but didn't earn a degree. Looks like you've got 33.1 million. Earned an associate's degree, 16.8 million. Earned a bachelor's degree, 17.5 plus 19.2, 36.7 million. And finally, earned some kind of advanced degree, a master's degree or a doctoral degree. Looks like we've got 10.1 and 9 plus 9.1, that's going to give us 19.2 million. All right, so that's the way the demographics of our sample space fall out with gender and and the level of education. So I want to try to keep that formula right here on our screen, right at the top. So a person is selected at random. What is the probability that the person is a man? So I'm going to call that probability of M for man. So we're just going to use this form, we're going to use what we learned before. This is a simple probability or simple event. How many men do we have in our group? Well, you can give me the probability for this. I don't have to put it together with you. Just give me the probability in fraction form. Yeah, we have 94 million men in our group and 195 million people in our group. So that's going to give us 0.482. We put that on our calculator. What is the probability that the person is a man with a bachelor's degree? Now this with right here is really and. The probability that the person we select is a man and this man has a bachelor's degree. So this is going to be the probability of man and bachelor's degree. So of course we have to look at the overlap there, right? So we have to go across the first row where they're men, stop at the bachelor's degree column, and how many are in, how many men with a master's degree do we have? Yeah, 17.5, awesome. Of course, we know we're going to divide that by the 195 million, and that's going to give us 0.090. to 3 places. Okay. Now, what is the probability that the person has a bachelor's degree given that he is a man? So we're looking at this formula right up here. The probability that the person has a bachelor's degree, that's B, given that he's a man. That's the A part right there. So from our formula, we know we want the number of outcomes in bachelor's degree in man. We know what that is. You just gave it to me. That's at 17.5. Divided by the number of outcomes in A. Yeah, and A is man. Yeah, so that's going to be divided by that 94. Good. So this is going to be, I'm going to write it down here. The probability of bachelor's degree, given that he's a man, is going to be the number of men who have bachelor's degree, 17.5, divided by the number of men. So what shows up in the second spot over here, the M, that's what shows up in our denominator. And when we put that in our calculator, we're going to get 0.19 to 2 places. All right, so notice that when we have the word given, I kind of teach it this way, and if it makes sense, go ahead and use it. If we've got the word given, what we're really given is a new sample space. Our sample space number changes. Notice that on every other problem that we've done so far with this table, we divided by 195. If we have an and probability, the probability of a woman and has an associate's degree, we're going to divide by 195. If we have an or problem, the probability that the person is a man or has an advanced degree, we're going to divide by 195. When we've got a simple probability, was a probability that the person was a man, we divided by 195. When we've got a probability that's conditional, we have a given condition, that's when we're given a new sample space. We're not going to divide by everybody anymore, the 195. We're going to divide by our new sample space, which is just the men. We're going to divide by that 94 million, or 94, because we just did it in millions. So whenever you've got a given in your problem, your probability problem, that's a conditional probability is the term that we call it. We're going to have a different denominator than we're used to having. We're going to be dividing by a different number because we know for a fact that we have a man. So that just wiped out all the women. We're not going to even think about those 101 million women. We're only looking at the 94 million men because we know we selected a man. All right, so the conditional probability rule actually gives us the last rule that we need for our discussion tonight. And the last rule that we need to talk about is the general multiplication rule. So we're going to compute probabilities using what we call the general multiplication rule. So the general multiplication rule goes like this. The general method for computing conditional probabilities provides a way to compute probabilities for events of the form A and B. So I'm going to take the equation that I gave you toward the top of the page. So I told you there that the probability of some event B given A, that's the way I wrote it up there, so I want to be consistent with my notation. The probability of B given some event A, I said that was the probability of A and B divided by the probability of A. So the instructions here say that we need to multiply both sides of the equation by the probability of A. So I'm going to multiply this side by the probability of A, and I'm going to multiply this side by the probability of A. So over here, the probability of A divided by the probability of A, that's going to be, they're going to cancel each other out. That's going to be 1. And I'm left with just the probability of A and B. And now I have a definition or a rule for the probability of A and B. I'm highlighting it right there. And I'm going to rewrite it for you down here. So if we multiply both sides of the equation by the probability of A, we get the general multiplication rule. So for any two events, A and B, the probability of A and B is going to be the probability of A times the probability of B given A. So I'm just copying that piece down right there. That's what we get. So let's take a look at an example here using that general rule for multiplication. So among those who apply for a particular job, the probability of being granted an interview is 0.1. So I'm going to call that the probability of I, the probability of getting an interview. That's 0.1. So I'm just going to translate that as I go along. Among those interviewed, so given that you get an interview, the probability of being offered a job is 0.25. So given that you get an interview, among those interviewed, the probability of being offered a job, I'm going to call that J, that's 0.25. I need to find the probability that an applicant is offered a job. So probability of being offered a job, of course, that's the probability of being granted an interview and then being offered the job. So that's where I'm going to use my new rule. That's the probability of I times the probability of J given I, according to my rule. So I replaced A with I because that's the interview, and I replaced B with J. That's the job. I was just using things that would help me remember what they were in the problem. So I know that the probability of being granted an interview is 0.1, and I know the probability of those interviewed. I know that the probability that they'll be offered a job is 0.25. And so when I multiply those two together, I get 0.025. Too many zeros. And if I wanted to think about that in percentages, about a 2.5% chance of getting a job if I apply for it. So there's an example of the general multiplication rule. Now, just like we had for addition, we had the general addition rule, then we had the addition rule for mutually exclusive events, and it was a little simpler. We have a similar thing with multiplication. There's the general multiplication rule, and then there's the multiplication rule for independent events, and it's a little simpler. So we're going to define what independent events are first, and then we're going to see what the rule is like. So two events are independent if the occurrence of one does not affect the probability that the other event occurs. If two events are not independent, then we say that they are dependent. So we're going to look at some examples here. Determine whether the following pairs of events are independent. So our first event is, here's a scenario. A college student is chosen at random. The first event is being a freshman. The second event is being less than 20 years old. So are the two events, being a freshman and being less than 20 years old, do you think they're independent I or dependent D? I'll take a little vote here. Dependent, independent, independent. Anyone else? I know there are a couple more of you out there. Okay, well, we'll take the answers from Alex, Jenna, and Christopher. Actually, Alex is right. These are dependent events. And Alex is happy. I don't blame you. That was a tough one. Great job, Alex. Yeah, that was a tough one. So, yeah, they're dependent because if I know that the person is a freshman, it's more likely that they're going to be less than 20 years old because your first year of college is your freshman year. So if I know you're a freshman, I know you're in your first year of college, the chances of you being less than 20 are going to be greater than, say, if you were a senior. Seniors at your last year in school. So what about these two events? A college student, again, is chosen at random. The events are born on a Sunday and taking a statistics class. Yeah, that's true, Christopher. There's nothing about independence that's or dependent that's necessary. They're just related. Yeah. So, and Jenna and Alex are saying that these are independent, and they're absolutely right. There is nothing in the world that relates what day of the week you were born to whether or not you're going to have to take a statistics class later in life. So let me see if I can spell here. Yeah. Independent. Yeah, and Christopher brings up a very important condition. None of this is necessary. It's just that the probability changes. You know, the probability of being a college student in less than 20, I'm going to make it up, is say maybe 0.20%. Say 20%. I'm sorry, 20% or 0.20. However, if I know you're a freshman, the probability of being less than 20 is going to shoot up. It might be 0.6 or 60%. It's not necessary that you're under 20 if you're a freshman. It's just that if I know you're a freshman, chances are greater you're going to be on the younger side. You're going to be less than 20. So it's not at all necessary. It's just greater than. And that's all dependent and independent is about. So we're getting to the rule now for independent events. Oops, we're going to look at a couple of examples here. So the multiplication rule for independent events. When two events A and B are independent, then the probability of B given A is the same as the probability of B. That's the definition of independence. If two events are independent, then the occurrence of one, the occurrence of event A, does not affect the occurrence of event B if they are independent. So the probability of B, given that A occurs, A has no effect on B, is the same as the probability of event B before A occurred, which is just the probability of B. Because knowing that A has occurred does not affect the probability that B occurs. So this leads us to a simplified version of the multiplication rule. For any two independent events, these have to be independent events, the probability of A and B is just the probability of A times, instead of the probability of B given A, we're just going to be able to write the probability of B because they're the same thing. So here's an example. According to the figures from the US Census Bureau, the percentage of people under the age of 18 was 23.5% in New York City, 25.8% in Chicago, and 26.0% in Los Angeles. If one person is selected from each city, what is the probability that all three of them are under 18? And is this an unusual event? So the probability that all three are under 18. So that's going to be the probability that the person from New York City, I'm going to call that probability NYC, is under 18. I'm sorry, oh, I keep forgetting my eraser doesn't work. Sorry about that. And the person from Chicago, I'm going to call that C, was under 18. And the person from LA, Los Angeles, was under 18. So all three, that's going to be an and probability. So according to my independent events, these events are independent. They're totally different cities. The census was taken at one point in time. So it's not like a young person could move from Los Angeles and be in the census in Los Angeles and move to New York City quickly enough to be in the census there. The census was occurring simultaneously throughout the United States. So we know that they're independent. So this is going to be the probability that the New York City person is under 18 times the probability that the Chicago person is under 18 times the probability that the Los Angeles person that was selected is under 18. So I'm just going to multiply the probabilities that were given in the problem. So the probability that a person in New York is under 18 is 0.235. The probability that a person in Chicago is under 18 is 0.258. And the probability that a person in Los Angeles is under 18 is 0.260. And so Alex is saying that we're getting 0.015. Is it 0.015 or 0.016, Alex, if we round to the nearest thousandth? 6, yeah, 6 if we round. That's what I had written down, and I didn't know if I'd made a mistake or not. Is this unusual? It is unusual, yep, because 0.016 is less than 0.05. Remember, that's what we define as unusual. Put another 0 in there if it helps. 16 is less than 50, so it's an unusual event. So what's going to happen on Connect Math this week in your homework? Sometimes you're going to be asked to compute a probability, and then you're going to be asked to answer the question, is that event unusual? And the test for unusual, is it less than 0.05? Is the probability less than 5%, if you're thinking of percentages? So that's just the definition that you kind of have to memorize. You'll probably use it enough that that will fall out quite easily for you. So we have some special examples, some examples I think that are pretty easy to understand for independent and dependent events here. And it's called, there are examples about sampling, repeated sampling with or without replacement from a population. So when we sample 2 items from a population, we can proceed in either of 2 ways. We can replace the first item before sampling the second. That's known as sampling with replacement. Oops. Let me see what I did here. Where am I going? Page layout. Maybe it's view. I hit something here, sorry. Oh, here it is. There we are. Okay. Sorry about that. I hit a button and it went all funky on me there. Okay, so let me get back down to where I was. So we can replace the first item drawn before selecting the second one from the population. This is known as sampling with replacement. Or we can, the other option is to leave the first item out when sampling the second one. This is known as sampling without replacement. So when sampling with replacement, each draw is made from the entire population. So the probability of drawing a particular item on the second draw does not depend on the first draw. When sampling with replacement, the draws are independent of each other. On the other hand, when we sample without replacement, the draws are dependent on one another. And we're going to see that in our next example. All right. So our example here. Andy is always looking for ways to make money fast. Lately, he has been trying to make money by gambling. Here's the game he is considering playing. The game costs $2 to play. He draws a card from a deck. If he gets a numbered card, 2 through 10, he wins nothing. For any face card, Jack, Queen, or King, he wins $3. For any ace, he wins $5. So we're going to construct a probability model for the game. So what's the probability that Andy draws a face card? Any of you card sharks out there? 52 cards in a deck, 13 cards in each suit. And there's going to be 3 face cards in each suit. So 3 times 4, 12 face cards in a deck. So what will our probability be as a fraction for drawing a face card? Well, okay, the probability is going to be a fraction because remember all probabilities are between 0 and 1. So if we have the jack, the king, the jack, the queen, and the king. So we have 3 face cards and we have 4 suits. We have the hearts, the clubs, the spades, and the diamonds. So we have 12 face cards in a deck. And I told you there were 52 cards in a deck of playing cards. We're going to take the jokers out. So 12 out of 52 would be the probability of drawing a face card. So see if you can use that example to give me the probability of drawing an ace. Think of how many aces there are in the deck of 52 cards. Good, 4 out of 52, awesome. And what about drawing a numbered card from 2 to 10? So you know what the sum has to be. We have to have accounted for all 52 cards because the sum of all probabilities are 1. So yeah, that leaves 36 cards to be the numbered cards. So 36 out of 52 is our probability of drawing a numbered card. So if you count 2, 3, 4, 5, 6, 7, 8, 9, 10, looks like there are 9 numbered cards in each suit. 9 times 4 is 36. 36 out of the 52 cards. So Andy plays the game 3 times. Suppose he returns the card to the deck after each play. What is the probability that he wins $5 on each play? So what does it mean to win $5? He has to draw an ace. So this is going to be the probability of drawing an ace and drawing another ace and drawing another ace. 3 aces if he's going to win for 3 times. He's going to play the game 3 times. So we said now he's returning the card to the deck. So this is drawing with replacement, and we just said that with replacement is independent. So that means it's just going to be the probability of drawing an ace times the probability of drawing an ace times the probability of drawing an ace, because he puts the card back and we shuffle the deck and he draws again. So when I multiply those 3 together, I'm going to get 0.0005. I can't help it, but is this an unusual event? Is it going to be unusual for Andy to win $5 on each one? Yep. This is a very unusual event, actually. That probability is very close to 0. So Andy may want to rethink his strategy here. I don't think he's going to make a lot of money at this. So part B says, Andy plays the game 3 times again. Suppose he does not return the card to the deck after each play. What is the probability that he wins $5 on each play? Well, the analysis is very similar, except for one key point here, which we're going to see. He's going to win $5 on each of the 3 plays. He's going to have to draw an ace each time. But this time he doesn't put the card back. So the first time, when he goes to draw from the full deck of cards, the probability of drawing an ace is 4 out of 52. But now Andy is holding an ace in his hand. He puts it down on the table. And if you're holding the deck of cards, you shuffle them up and you fan them out so that Andy can choose a second card. How many aces are left in the deck if there's an ace on the table? Yeah, 3 aces in the 51 cards that are left in your hand. And so that's the probability that he draws a second ace. So now we've got 2 aces sitting on the table. You've got 50 cards in your hand. You shuffle them around and fan them out. And yep, there are 2 aces left in the cards you're holding, out of the 50 cards you're holding. So you can see that this is the dependent case. So if we're not going to replace the card, the probability on the second draw depends on what we drew first, because there's a card that's not in the deck. And so we have to take that into account when we're figuring those probabilities. So when we multiply those together, we get 0.0002. And of course, this is even more unusual than the first way of playing the game. So yeah, so if Andy's thinking he's going to make big bucks here, he thinks he needs to reconsider. But the purpose of that was to show you the difference between dependent and independent situations. A lot of times we're drawing, I don't know, ball bearings from a lot of 100 ball bearings that have been shipped to us. We know that 7% of them are supposed to be defective. So 7 out of those 100 ball bearings are going to be defective. These problems often tend to work that way. So you'll see this example in some of your homework problems, just maybe under a different story. The last type of probability, I believe, that we need to go over tonight is the, yes, it is the last one, it's the at least one case. So the at least one case is,
Hey, Elizabeth.
Goes up. Yep.
Sorry to interrupt, but when it looks like when we multiply those in our TI-84, it came up 4.548930.769 with a capital E and a -4.
Yeah, let's take a look at that. Thanks for asking that, because yeah, that's something I should address here. Was that the last one that came up that way, Chris?
No, that was the
The
first
one before, the first one. Okay, I just wanted to get the right problem. So this is what Chris is saying. When we did that first problem, we did the 4 times out of 52 times 4 divided by 52 times 4 divided by 52. Yeah, this is the number that Chris is talking about, I believe, that 4.55166136 E -4. So what that is telling us right there, I'm going to write it out here. And I'm just going to round, I'm going to do 4.55. I'm just going to round that part to the nearest hundredth. So we've got 4.55, and I'm just going to put ... because I'm not going to write all of that out. E -4. That's in what we call scientific notation. So what this is telling us, that E is the exponent on 10. So this is 4.55 times 10 to the -4th. Now, when we multiply by powers of 10, we just move the decimal place around. If we multiply by a negative power of 10, so -4 says we're going to move this decimal point 4 places to the left. So this is going to be 0.000455. If I move that decimal point 1, 2, 3, 4 places to the left because of that -4 right there. So that 5 tells me to make that 4 a 5. That's where I'm getting that 0.0005 that I told you about. And that will happen in some of our very unusual probabilities. They might be presented in scientific notation. So again, just so you have a chance to see what scientific notation looks like, whenever you see an E out there, you're going to have to interpret that number for me. So you can't write 4.55 down as your probability, because we all know that probabilities are between 0 and 1. So we know that 4.55 can never be a probability. So if you see a number bigger than 1, keep going because there's going to be an E negative something at the end of that number, and you're going to have to interpret it for me. Does that make sense, Chris?
Yes.
Yeah, does it? Okay, good, good. And everybody, I'm so glad you pointed that out. I need to leave myself a note here. Review scientific notation. I'm doing that on my notes right now. I'm glad, because sometimes this is going to happen to you on your homework this week, I think. I just want you to be prepared for it. Okay, got it. All right, so the at least one type of probability. So sometimes we need to find the probability of an event, that an event occurs at least once in several independent trials. So we're going to make this kind of simple here. They're going to be independent trials. So let me just get the chat box up here again. Okay, yeah, so all of you are getting that weird number. Good, glad we got that taken care of. So sometimes we need to find the event. We need to find the probability that an event occurs at least once in several independent trials. The easiest way to calculate these probabilities is by finding the probability of the complement. So we're going to look at an example here. And this at least problem is going to come back to haunt us next week. So you'll get a little bit of practice with it this week, and then we're going to really pounce on it next week. So kind of getting ready for something here that we're going to talk about next week when we get to the binomial probability distribution. So a fair coin is tossed 5 times. What is the probability that it comes up heads at least once? So we want the probability of at least one head. I'm going to abbreviate it that way, in 4 tosses, in 5 tosses of a fair coin. So what does that mean? That's a probability of 1 head, or 2 heads, or 3 heads, or 4 heads, or all 5 are heads. That's what at least one means. 1 or more heads. So remember, we're tossing the coin 5 times. So the probability of 1 head and 4 tails, 2 heads and 3 tails, 3 heads and 2 tails, 4 heads and 1 tail, 5 heads and no tails. All of those events are in what we want. What is the only thing we're leaving out? What's the only outcome that we're leaving out? What could happen that I haven't listed here?
All tails.
All tails, yeah. So the complement of A is 0 heads, and I'm just using that as blank. It could be, we have a family of 5 children. What's the probability that we have at least 1 girl? Okay, you can fill in the blank. We're tossing a coin 5 times. What's the probability we have at least 1 head? You know, so this can take on lots of different scenarios, same problem, just different words, different stories for it. So the probability of at least, the complement of at least 1 is always the complement of 0. Now we know the complement rule. What we want, the probability of at least 1 is 1 minus the probability of its complement. Now 0 heads, that's pretty easy to figure out. That's going to be 1 minus, well, the probability that we toss tails on the first toss, that's 1/2. And so we're going to multiply tails on the second. Tossing a coin is independent. The coin has no memory. It doesn't remember if it landed heads last time or tails last time. It can't throw itself to land on one side or the other. It is totally independent as far as we know. So these are pretty simple probabilities to calculate. So there's heads on tails on the second, and tails on the third toss, and tails on the fourth toss, and tails on the 5th toss. I'm just going to use a little notation here. This is 1 minus 1/2 times itself 5 times. So that's what we use exponents for. And let me show you how you can get that on your calculator pretty easily here. So I can do 1 minus, and then in parentheses, put 1 divided by 2. And then this little caret right above the division key, that little caret key, that's my exponent marker. And I'm going to put to the 5th power. And that's going to be 0.969 actually, if I round to 3 places. That 7 says to make that 8 and 9. So 0.969. It's very likely that I'll get at least one head in 5 tosses of a fair coin. So we always approach at least one.
Where was that caret key? I looked down away from the thing.
Oh, did you? Okay, the caret key is right here above the division key. So find the divided by key and then look at the key above it. That's the caret key that I used. Right there. And thanks for using the mic on those things. I don't always can't always keep up with the chat box there. So that's great. All right, so that takes us to our next steps. Listen to the interactive, the multimedia assignment, the interactive lectures for Module 4. Remember that has to be done by end of day Thursday. Then we have the usual, complete the practice homework assignment with at least an 80%, complete the homework quiz with at least, well, you only get one crack at that, so the best you can do. Those are due by end of day Sunday, and the application assignment is also due by end of day Sunday. And I want to look at the application assignment with you here before we go tonight. We're going to go to the casino, actually, not literally, but in our assignment we are. And I just wanted to go through a couple of, especially for that first scenario, playing craps. Just want to make sure you understand how that is written. Also, I wanted to tell you too, if you don't get the 80% in 3 tries on the practice homework, shoot me a quick email as long as you have time remaining, or even if you need it to turn it in a little bit late, that's fine too. Send me an email and I can increase the number of times you have on the practice homework. So, you know, if you've done it 3 times and you just missed 80, or maybe you missed 80% by a lot, just send me an email to ask me to increase the number of tries and I can do that. So you're not blocked out if, you know, if you've got enough time, you're not blocked out by not being able to get an 80% on your practice homework for that. So I want to make sure you knew about that. So here's what our application looks like for this week. In this assignment, we are going to use probabilities to examine some popular casino games and to determine how different a consumer product is between men's and women's versions. So we're going to be doing a couple of things in this particular assignment. So the first one is the one that I wanted to go over with you because sometimes people have trouble interpreting craps. And I think the way this has been written, I'm not much of a gambler myself, but I've got a couple of friends at Columbus State who are avid gamblers, and they have kind of explained craps to me. So I'm going to try to do my best here. And if some of you are familiar with craps, what you're going to notice is that it may not be stated the way that you're used to playing it. So we have a favorite casino game of craps is played in the following manner. A player starts by rolling a pair of balanced dice. If the roll, the sum of the 2 numbers showing on the dice, that's what we mean by the roll, results in a 7 or 11, the player is going to win on the first roll. If the roll results in a 2 or a 3, that's called craps. The player loses on the first roll. For any other outcome, the player continues to throw the dice until the original roll reoccurs, in which case the player wins, or until a 7 occurs, in which case the player loses. So if I'm playing craps and I roll a sum of 5, okay, I didn't win, I didn't lose on the first roll because I didn't throw a 7 or 11, that would make me win. I didn't throw a 2 or 3, that would cause me to lose. I threw a 5. So I keep rolling until I roll another 5, in which case I win. Or if I roll a 7 and it's not on the first roll, I automatically lose. So if I roll a 5, then I roll an 8, then I roll a 7, I've lost. However, if I roll a 7 on the first roll, I automatically win. That's where people who are unfamiliar with the game, they kind of miss that point. So what you see down here, we're just going to talk through a couple of these together. What you see down here is your sample space. So your first die is red, your second die is white. We talked about rolling a sum of, let me see if I can get my pen back up. We talked about rolling a sum of 2 or 3. So here is what will lose the game for me, those 3 outcomes. We talked about rolling a 7 or 11. Well, here are my 7s, right up the middle diagonal. And here are my 2 11s. What I've outlined in blue, that's going to win the game for me. Anything else, I'm going to have to continue. So what's the probability that a player wins the game on the first roll of the dice? Well, how many outcomes did I circle in blue? How many total outcomes? Yeah, 8. So 1, 2, 3, 4, 5, 6 7s and 2 11s make 8. 8 out of how many outcomes are there if I roll 2 die altogether? Yep, 36. So there's your first answer. We did it together. Write your answers as a fraction for me, please. And then if you like, you can write them as a decimal, but I don't think you have to. The instructions didn't say you had to. If you were going to do that, 0.222 to 3 places. But what I prefer is I like to see the fractions, because the fractions are really your work. If I see the fraction, then I know if you got the sample space right, if you got the 36 right, if you got the number of outcomes in the event right. That gives me some information about what you were thinking. If you just give me a decimal and it's wrong, I have no clue where that came from, and I can't give you any feedback. So that's the trade-off there. If you at least give me your fractions, I can give you some feedback. So the rest of it, I think, is pretty straightforward right there. I think we've talked it through on that. I just want to show you how it worked. It looks like we've got a car inventory that we're going to be working with. So this is going to be a lot like the problems we did with the men and the women and the types of degrees they had. So this is just going to be one of those, drawing from a sample, get your totals together like we did in that problem. That problem that we did about the genders and the bachelor's degree and master's, and graduate degree and, all that kind of stuff. That's a good example for this problem right here to pattern it off of. And here you are going to be writing your answer as a fraction and as a decimal. They changed it, wouldn't you know, up to 4 decimal places. So you'll be rounding these to 4 decimal places. They changed that. That used to be a 3. So just pay attention to your instructions. And then here we're going to be looking at, are they really different? So we have many, so with so many men's and women's versions of different products like shampoo, hair coloring, that kind of stuff, colognes and that, you might wonder how different they really are. To help answer this question, technicians at Consumers Advocate compared a new antiperspirant for women, that's event A, with a leading antiperspirant for women, that's B, and a leading antiperspirant for men, that's C. A randomly selected group of 30 women consumers were asked to use each of these products over a 3-week period, 1 product for each week, following a random design. So they randomly assigned the treatments. At the end of each week, the women were asked to rate the antiperspirants on a 5-point scale, with 1 being poor and 5 being excellent. And here is the following table that contains a summary of the results for these questions. So these are the number of women who gave these ratings for antiperspirants A, B, and C. So you're going to be answering questions. Again, it's going to be very much like a table problem, but just make sure that you read your headings here so you know what you're talking about and you know the types of antiperspirants. And these questions should be very straightforward. They're going to be numbers from the table again, just like we did in some of our examples. So I think that takes care of it. Yeah, that takes care of the assignment. So any questions from you guys before we call it a night?
No, thank you.
No, you've got it. Okay, good. Good. Well, if you do have questions, either jump in on the mic or